and we will select that attribute. So, we are trying to determine the information gain on using a particular attribute, and we will split the examples on the selected attributes possible values, and we find the difference in the information content of a node and the information content after the node is split. And as I mentioned that to measure the information content of a set of examples S, we will use the concept of entropy. Suppose S is a sample of training examples that we have. S is the sample of training examples that we have, and let us say in the sample S, P is the proportion of positive examples, N is the proportion of negative examples. Entropy measures the impurity of S. It is defined to be minus P log P minus N log N, where P is the proportion of positive examples, N is the proportion of negative examples, logarithm is to the base 2. So, this definition is if we have only 2 classes. In general, if you have a number of classes, then entropy of the set of examples is defined to be minus sigma of Pi log Pi, where Pi denotes the probability, Pi denotes the fraction of examples which belong to class Ci, okay, and we sum it over all Ci. So, this is the general definition of entropy when you have arbitrary number of classes. Now, the entropy function can be plotted for the 2 class problem as shown here. This is an approximate shape of the entropy curve. We have plotted entropy on the y axis with the value of P on the x axis. We see that when P is 0, entropy is 0, when P is 1, entropy is 1, and the curve has a shape like this. So, we see that we see that the entropy is maximum when P is half. When P is half, entropy is 1. When P is 0 and 1, entropy is smallest. So, the impurity of the data is maximum when P is half, that is we have exactly equal number of positive and negative examples, then the impurity is maximum. Impurity is smallest when either P is 1, that is all examples are positive, or P is 0, that is all examples are negative. If P is half, we have a mixture. So, entropy is a measure of the impurity. In information theory, entropy is actually interpreted as the expected number of bits to encode a class. Suppose you have 2 classes plus or minus, and you get randomly drawn examples of S. Entropy denotes the expected number of bits to encode a class. Suppose all the class is positive, then you require 0 bits to indicate whether the object belongs to a positive class or negative classes, because you know all classes are positive. If all classes are negative, also the same thing will happen. If classes can be either positive or negative with equal probability, you can use 1 bit to encode the classes as 0 or 1. Suppose positive classes are more frequent than negative classes, what you can do is that you can choose an encoding so that a positive class uses smaller number of bits than a negative class. So, patterns involving positive classes will be more likely, and to encode them you can use smaller number of bits. So, information theory, we find the optimal length code, and it is found that if a message has probability p, then you require optimally minus log p bits to encode that message. So, the expected number of bits to encode a random member of S by information theory is given by minus p log p minus n log n, which is how entropy is defined. And we will use this concept in deciding the information content of a set of examples that we get in a decision tree. So, entropy characterizes the impurity of a collection. So, just to give an example, suppose S is a collection of 6 positive and 4 negative examples. Entropy of S can be computed as minus 6 by 10 log 6 by 10 minus 4 by 10 log 4 by 10, which can be evaluated to be 0.97. If the target attribute takes m different values, that is there are m classes, then the entropy of S with respect to the m-wise classification is defined as minus sigma pi log pi. We already discussed this, where pi is the proportion of S belonging to class Ci. Now, how would we use information gain to select the best attribute? So, we introduce the concept of remainder A. So, suppose we have a set of training examples S, we can find its entropy. Now, when we classify using A, we split S into different subsets. We define remainder A as the weighted sum of the information content of each of these subsets. So, S is partitioned into subsets by possible values of the attribute. Remainder A is the weighted sum of the entropy of these subsets. So, remainder A can be taken to measure the total disorder or inhomogeneity of the children nodes when you classify using the attribute A. So, the expected reduction in entropy caused by partitioning the examples using the attribute A is given by gain SA. So, gain SA is defined to be entropy S minus remainder A, and remainder A is weighted sum of entropy SV. SV is the subset of S for which the value is V, and we sum it over all values of V. All V is all classes that we can have, all attribute values that A can take. So, we define the best attribute to be the attribute for which gain SA is maximum, or equivalently for which remainder A is minimum.